Hey everybody, welcome back. Today, we're going to take a slight deviation from our usual rhythm of alternating lectures and discussion, with another lecture introducing some concepts of parallel programming. And we need this because it's going to help us do more in the same amount of time, or do more maybe even in less time for some of our simulations. So we're going to talk about that today. We're going to postpone any discussion of the network stuff, the network exercises from last class until Thursday, when we'll have another live session. As today's is a pre-recorded lecture, I do urge you to go ahead and ask your questions on the Ask Tutors channel. We will get to them via Slack as soon as we can. And then we'll open Thursday with a discussion of any lingering questions from this. And then we'll address the homework from last Thursday and the homework from today. With that, let's get started. Now you might wonder, why should I even bother with parallel computation? There's actually several reasons for this. Perhaps most obvious is that we may want to get the results for a simulation in less real time. So imagine that you have a meeting with your advisor tomorrow, but you have a set of analyses that you want to run that are that a best case scenario are going to run in one day. Well, if all goes perfect, you're golden. But if something goes wrong and you need extra time, you don't have a whole lot of slush there. But if you could speed up your simulation by a factor of 2, a factor of 4, a factor of 8, who knows, depending on how much compute resources that you have available and how well the model scales, you're better off running it faster, getting the results faster, so you have time to do analysis. Equally important, though, you may want to run a larger simulation the same amount of time. So let's say that you're doing a long-running set of analyses, and is it better to look at a 100 neuron network or a 1,000 neuron network? And the answer to this may actually depend, of course, on your specific problem, but you could imagine that if your model is too small, you may have some effects that really come down to the small number of neurons rather than the actual understanding of the actual underlying dynamics. So to avoid that, maybe you want to run larger simulations, capture using more cells, or run them at a higher spatial or temporal resolution so that you can reduce some error. Now, of course, I should mention that when you do this, when you do parallel simulation, there's normally some communication overhead. So you're splitting up your model to run across multiple compute nodes. If you're using an HPC, these may be located on physically separate machines, but you could of course do this. And to be clear, this also works on your laptop, or you probably still have 4 cores on your laptop, and so you may want to take advantage of Neuron's support for parallelization to speed up your calculations on your laptop as well. But here's the fundamental thing: every time that the fundamental issue with parallel programming in general is that communication is costly. Every bit of communication that's required is going to slow down your simulation. Now, we saw from last class, Ted's presentation, that it is in fact possible to communicate less often than you might think we need to, because of all of the delays between when a spike is generated and when it has an effect on a downstream cell. Nonetheless, you'll actually get the best possible speed up in the case where you're doing, say, parameter sweeps, where maybe instead of just trying to speed up one simulation, we go ahead and accept that an individual simulation runs at a certain speed, but we spread out the calculations, and so that every core maybe is solving a different problem with a different parameter value. We've mentioned before that Python's multiprocessing module will do some of this for you. You can also take advantage of MPI, and Neuron provides a bulletin board system that allows you to get the same effects but across an HPC. And this is the ideal, in some sense. This is what's known as an embarrassingly parallel problem, because there's no need for any of the processes to communicate, because they're all solving separate problems. And so you'll get the most potential speed up from just running more simulations simultaneously. Finally, I should also point out that sometimes if you have really big models, they're not all going to fit on one machine. Hopefully you've parameterized your model and you've built a smaller model and you've tested that smaller model before you get to this point. But if you just have something that doesn't fit in memory, then there's nothing else to do except to use a HPC system and distribute it so that every compute node is only storing in memory its portion of the problem, and then so therefore there's no more memory issues. Now, I will say, they say that, as they say, there's no such thing as a free lunch, and parallel programming is no exception. Although Neuron tries to make this as easy for you as possible, it does still introduce greater programming complexity, although you can largely mitigate this, most of this, if you build your models from the ground up with the assumption that they're going to be run in parallel. Maybe not today, maybe not tomorrow, but eventually. There is also the potential to introduce new types of bugs, especially if you're dealing with random number generation, for example. You want to make sure that you're going to get the same results no matter how many compute nodes you're running on. And so you have to think about how you pick random numbers in a way that allows you to do so. And it is going to take you a little bit more time because a little bit more effort, a little bit more care. There's a new potential for bugs. And so you have to decide if the time that you spend parallelizing things can be recovered. Are you going to actually come out ahead and get your results faster? However, here's the thing. If you're actually running a large model on a large system, so let's take the old 16,000 core Blue Gene Ps, all right? Those were, any individual core on that system only ran at 850 megahertz. But if you compare that to a 3 gigahertz desktop processor, 16,000 cores at 850 megahertz is in theory doing as many calculations as a 3 gigahertz single core machine can do in 6 months. So there is a huge potential for speed up. And as you may know, your university likely has its own HPCs. There are often national, so for example, Exceed within the United States, or regional, so the Ohio Supercomputing Center within the state of Ohio. So similar things exist in Europe and elsewhere throughout the world. I'm just less familiar with them. So you often have tremendous access to compute resources that may not, and also I should point out that there's the Neuroscience Gateway. So even if your own personal machine only has 4 cores, that doesn't mean that you don't have access. You can't get access to larger resources for speeding up simulation. All right, so, and we sort of hinted at this. There's 3 main classes of parallel problems. You may want to do a parameter sweep. We've already discussed this. You can do this with multiprocessing module or MPI using Neuron's bulletin boards. These are embarrassingly parallel. There's no communication required. Alternatively, you may want to have a parallel model that where it distributes networks across processors. The most efficient version of this is when it's reasonable to have any individual cell entirely on a single processor, but maybe the cells themselves are distributed across tens, hundreds, thousands of processors, how many that you have. And in this case, there's exactly how this works is going to depend, and how efficient this is going to depend on the nature of communication between the cells. So for example, last class, we talked about logical spike events. So a cell generates an action potential that triggers a netcon. That netcon then has a certain delay, and it can send this information to whatever machine owns the postsynaptic cell at any point before that simulated delay period ends. So that's going to allow fairly efficient communication because we can exploit these delays. Alternatively, however, they may communicate via postsynaptic inductance that depends continuously on presynaptic voltage. So sort of a continuous process as opposed to a process that involves delays. This is obviously going to involve much more communication between compute nodes They may communicate via gap junctions. We've also sort of hinted at the existence of extracellular mechanisms, so extracellular reaction to fusion, for example. Cells may communicate by modulating chemicals in the extracellular space. There again, you have to simulate basically and communicate between compute nodes basically at every time step. And again, this is in contrast to these sort of chemical synapses that use logical spike events, which are much more efficient. Alternatively, you may want to try and distribute single cells across processors using what's known in neuron as the multi-split method. And there are papers on this, and you can look up. Go ahead and ask on Ask Tutors if you would like to know more. Again, this of course requires continuous communication at every time step, but it may still speed up your model if it enables what's known as load balancing and allows each processor to advance at comparable paces. And any individual parallel model can use any sort of one, two, or all three of these classes. That's fine. Just a couple of bits of philosophy before we really get into this, though. When you remember that, of course, these networks are composed of many individual neurons of potentially many cell types. And as best as you can, you're going to want to design and debug every cell type independently before building the network, right? If your cells aren't doing the right thing, then your network's definitely not going to do the right thing. You're going to want to make sure that your simulations give the same results regardless of the number of processors used to run it, right? It shouldn't matter. You should get the same thing if you use one compute node or 1,000. One way of sort of testing this, I mean, so if you have a big model that's just not going to run, you know, you're like, why? How can I tell? I need the big network. Well, if you've parameterized your network in such a way so that maybe it scales in some way with the number of neurons, maybe you can test it with a small number of neurons first. And then does your small number of neurons that presumably runs network that presumably runs much, much faster, does that give you the same results as you go from 1 to 2 to 4 cores? If so, that's a good sign. If not, that's a problem. And you may wonder what could cause this to go wrong. And well, there's any of a number of reasons. But I will point out one of the things, I point out, for example, if you have any sort of randomness in your model, you're going to need to think about how you grab those random numbers to make sure that you get them consistently, no matter how many processors are involved. And we'll talk about how to do that. But the short answer is using a thing known as random 1, 2, 3 in Neuron, which is a tool designed to generate parallel independent random number streams. So fundamentally, one of the big conceptual things that I would like to suggest that's not strictly required for networks, but is going to be required anytime that we do parallel simulation, is to identify every cell that we create with what's known as a GID, a global identifier. And we can do this by, in our cell class, passing in our identifier and just storing it within the cell. Everything else here should look fairly typical. Here I'm not using an F string, but this is another way of putting that identifier inside of here. So if I constructed this pyramidal cell with a GID of 1, it would print out as pyramidal square brackets 1. All right. And so we're going to want this GID to be it's a unique identifying integer. And we're not going to have these auto-generated within the cell class for 2 reasons. First of all, because if every processor is running them independently, they have no way of knowing what exists on other processors, except by some logical rule. So the cell class can't be responsible for auto-generating numbers. And also, just because we do a network simulation doesn't mean we'll never want to go back and look at any individual cell in isolation. We've pointed out in the past, and I'll point out again today, that if you have a network that's driven entirely by chemical events that are, the event-based netcons, then if you know where a cell starts and you know all of the events that modulate the cell's activity, then you can construct each cell independently and run each cell independently and analyze whatever you want without having to rerun the entire network. So again, then the cell needs to be well-defined on its own, independent of the network. And so you may wonder, well, that doesn't seem like a big deal, but imagine you might have some randomness that's involved. So I want to make sure that cell number 5 is always going to generate the same dynamics, regardless of whether or not the network exists. Right? Cell 5's randomness, cell 5's, maybe its morphology is random, maybe its synaptic weights are random, maybe its conductances are random. Who knows? But whatever is random, whatever is unique about cell 5 needs to be defined simply by the fact that it knows that it's cell 5. All right, so you can construct that. So that's the big key here. Whenever we define our cells, we're going to give each cell an identifier. It's going to be an integer. As we do this, of course, you're going to go ahead and discretize, declare channels, set parameters, as usual. And again, remember last Tuesday we talked about d lambda as a principled way of getting a first estimate for what's a decent spatial scale. And of course, within each individual cell, you can always go under Tools, ModelView if you're using the GUI, and get a graphical exploration of the properties of the cell. And even if you're not otherwise running the GUI for your big simulation, certainly you're not going to use the GUI for the actual parallel simulation. But even if you're not, it's still nice to be able to construct a cell and look at it within the GUI to see, does everything look the way that you expect? All right. So that's so far the main conceptual thing though is every cell must have an identifier. Now, one other major conceptual difference though is if we are running a simulation, we're going to use what's known as a parallel context tool, or h.ParallelContext, as we run this. So this should look fairly similar here. Where from neuron import h, from matplotlib import pyplot. Pyplot is just a graphics library. Matplotlib is just a graphics library. It's kind of like Plotly or ggplot or whatever you like. Load the standard run library. We can now, when we construct a single pyramidal cell, we have to pass in that identifier. So this is constructing pyramidal 0. As always, of course, then if I want to put a synapse somewhere, I can say my pyramidal being my cell object dot den0, right? So that's going to be the 0th dendrite section, the center of the dendrite, and that particular pyramidal cell, not for all the others. So there we go. I can construct a postsynaptic thing and add a certain reversal potential. So it's a reverse potential of 0 millivolts. So that's going to be an excitatory synapse. I'm constructing that stem to stimulate my cell. We've been doing this for weeks now. I'm going to just generate a single spike. It's going to happen at time 3 milliseconds. A netcon could connect my stimulus to the synapse. I'll give it a certain delay and a certain weight. We'll see in just a moment, well, as we see over here, is a rather strong weight. And so when that comes on, it's going to the membrane potential is going to rapidly rise, but then eventually we will see sort of the more standard action potential looking shape. We record, but now when it comes to running, we're not going to use finitialize, and we're not going to use continue run. Instead, we're going to go ahead and construct what's known as a parallel context object. PC is h.ParallelContext. And basically, most everything that you're doing in Neuron that involves parallelizing a simulation is done through a parallel context object. So here, for example, we now set a maximum step. And what this is doing is this is saying that no matter what happens, I need you to synchronize at least every 10 simulated milliseconds. If you don't set a maximum step, the simulator will yell at you and your simulation will not proceed. It's not saying that it will wait 10 milliseconds to synchronize. It's simply because it will look at all of the synaptic delays. And so see over here, for example, it sees that there's a synaptic delay of 1 millisecond. And that means that it will actually synchronize every millisecond. Nonetheless, this call is required to allow initialization. To allow simulation. One moment. Now, in lieu of doing a h.f initialize of, say, -69, here I'm going to use std init. I actually don't think that this is necessary, but this is an alternative way of initializing a simulation. So here I'm going to run this set of membrane potential that I want to initialize to be -69, and then std init is going to basically do the f initialize call, and it's going to use whatever's in vnet. I'll get back to you on Thursday about whether or not this is necessary, but I don't think so. I think you can just do a regular f initialize. But finally, what you can't do is you can't do a continue run. Instead, we're going to use the parallel context and the psolve, or parallel solve, pc.psolve 10. And what that does is that's going to run our simulation until time 10 milliseconds. And I would have shown this, I would have introduced this instead of continue run, except it does have this mild inconvenience of needing to do the max step. So it is an extra step that really doesn't make a lot of sense if you're only running a single-threaded simulation. But you can run this for single thread. Like, we haven't actually told it to parallelize anything. There's only one cell. There's nothing really. In fact, there's only one segment of one cell. There's literally nothing that we could parallelize. But in any case, so once we've done this, we can plot T and V, give us some labels and plot it. And so there we go. As we see, we have an action potential, and we also see that the synaptic weight is extremely high. So, okay, this is all, however, very familiar looking, except for this little bit in blue here. How can we actually construct synapses between the cells? So let's again focus on these netcon style synapses. So imagine, for example, that I have cell 7 is going to be my presynaptic cell, and it wants to send a message to cell 9. So first of all, we're going to construct our cells only on the right processor. So CPU 2, let's say, needs to know that it owns cell 7. If so, and you can actually have each cell register, and we'll see this in a moment, we'll have each cell register its existence with parallel context. And then so you can have, so if node 2 knows it for other reasons, that's cool. And if not, you can ask the parallel context object, hey, do I have cell 7? And if so, go ahead and construct the cell. So CPU 2 never needs to know anything about the postsynaptic cell per se. It's just going to say, hey, do I own this cell? If so, then I'm going to build it. If it doesn't, I'm not going to use any memory for it whatsoever. And this is how parallel context can save you memory, and when you're doing these large models over distributed systems. Okay, so what I'll do now, though, is I will say, well, okay, I want to connect to netcon. I want it to go from 7 to 9, but I don't actually own 9, so I can't put a point. I certainly can't refer to this postsynaptic object that's on 9. So instead, on the source, on the presynaptic side, I'll just say I'll have a netcon that starts with that presynaptic thing. So that's typically going to be a pointer. And then we're going to need to give the section. All right. And then where does it go? It goes nowhere. So this is exactly the type of netcon that we would use if we were wanting to record during a net, that is with the netcon.record, if we wanted to record a spike events. But here, however, we'll just say that some number, the GID, is going to be associated with that netcon. And then so every time that netcon gets triggered, Neuron will identify that as, oh, cell 7 is spiked. Well, how are we going to connect to a different machine that doesn't even have doesn't have the pointers to the presynaptic side, doesn't own the netcons. Well, that number is going to be our key. What makes this possible is on the postsynaptic side, we'll use the parallel context object and we'll use a .gid connect. And then so we're going to say, hey, you remember that input from cell 7? You don't know anything about cell 7, but trust me, there's a cell 7. Remember that input from cell 7? Yeah, now we're going to send that to the postsynaptic side. And this is going to return a netcon object. And once we have that netcon object, we can work with it. We can set the weights. We can do all of those things that we're used to working with netcons, but on the postsynaptic side. So again, here postsend is going to be some sort of point process, like an exp send, exp2 send. There's also, you'll find within ModelDB, you'll find, GABAergic, AMPAergic, all of these things that are NMDA, all these things that are pre-tuned for various things. So let's look at how this happens behind the scenes just a little bit more. So imagine on the presynaptic side, I have an action potential and it crosses my threshold at a certain time, 2.875 milliseconds. And I know that all of the synaptic delays are at least 2 milliseconds. So what's going to happen is that all the communication is going to happen at either time 0, time 2, time 4, time 6, 8, 10, etc. every 2 milliseconds. So I'm just going to take a note. I'm going to say, oh, well, there was a spike at time 2.875. And nothing has to happen. There's no overhead just yet. I have until time 4.875, since I said it's at least 2 milliseconds, to get around to telling my postsynaptic cell. So what I'm going to do, however, is when I hit that 2 millisecond time point, because I'm not going to base my time points, I'm not going to base my communications on the actual spikes, I'm just going to base it on the minimum because that's the time. That way I don't, because the other processors don't know when the spikes happen yet. But they know, oh, well, we're just going to agree. We're going to synchronize every so often. Cool. So when we hit that next synchronization point at time 4, what happens behind the scenes is an MPI altogether. If you don't know what this means, don't worry about it. But in any case, all of the processors are going to tell everybody about all of their spikes. And then so what that means is that CPU 4 is going to get some information from the second compute node saying that, hey, by the way, cell 7 fired at time 2.875 milliseconds. And then as the simulation continues to advance and we get to time 4.875 milliseconds, let's assume that that was in fact our synaptic delay was exactly 2 milliseconds, then that event will be delivered to the postsynaptic thing. So that netcon will be triggered, that event will come in, the postsynaptic cell will respond according to whatever the synapse rules are. So fundamentally now we have, I think, 3 concepts, right? First of all, every cell needs a GID. Second of all, when we're running anything in parallel, we have to call this set maxstep. As I said before, and hopefully now that we've seen how Neuron actually does this by communication, it makes a little bit more sense. But set maxstep is going to affect how the interval at which Neuron communicates. So larger is better in many senses, but it cannot use anything bigger than the delay. So Neuron will take the minimum of whatever your set maxstep value is and the synaptic delay. So we have to set the maxstep whenever we run it, and then we run with psolve. We do not use continue run because psolve sets up the infrastructure, does all the communication to figure everything out. So every individual process is going to be using a set maxstep and a psolve. Right. And so also we talked about altogether for the spikes. Set maxstep uses what's known as an all reduce. Again, it's the communication between all of the processors because not everybody knows all of the delays, but collectively they do. All right. Now let's go back a little bit. Let's think about this a little bit more. When we're constructing our cell class, I mean, again, remember, always store the GID. You know, honestly, most of these cells, and we talked about that there can be exceptions. You know, mitral cells using dendrodendritic synapses might be an exception, or well, there's lots of potential exceptions. But generally speaking, action potentials are highly stylized, right? The cell fires, and then it's going to be propagated down further along. So in many models, maybe most models, you only need to determine the time that a cell fires once. You don't need to monitor lots and lots of locations. So it is meaningful to say cell 7. You could, if you have to, say a specific location on specific cells, and then each one gets its own GID instead of the cell. But like I said, for most practical purposes, we'll just say we'll identify GIDs with the cell. So when we're doing this, let's just go ahead as we construct our cell. Let's just go ahead anytime we construct a cell to go ahead and create a netcon. And so that netcon will, you know, maybe monitor the cell membrane potential or the axon initial segment. You'll have to decide where it goes nowhere, needs to know the section and as well as the pointer. And then so once we've created that netcon, we'll construct a parallel context object. This can be thrown away when we're done. This is just simply to give us access to the underlying machinery. And we'll identify that, hey, by the way, this GID is going to belong to whatever identifier. So I'm going to go ahead and construct my netcon, claim that I own this pc.id is whatever my processor number is. Right, so I, the current running process, am going to own this GID, and then pc.cell is going to map the GID and the netcon object together. You must call this set GID to node before you invoke pc.cell. All right, so it's pretty much always going to look more or less like this. So you could imagine that you could use this, and if you wanted to build a network, we might construct a network object. And so my network object might have a list of cells where each cell is individually also an object, right? And then I might have synapses that are properties of my networks, and each synapse belongs to a given cell. So here I'm going to construct a list of synapses, one for each cell, and that cell's center of the dendrite is going to be an exponentially decaying synapse. And then I'll set all of their all their reversal potentials to 0 millivolts. And then I can connect my network together within my network class here by creating that parallel context. All sort of parallel related things, and this includes connectivity, are done through the parallel context object. And I'm just going to map a presynaptic cell to the postsynaptic cell synapse with a certain delay and a wait. And you see here, I get my netcon from pc.gid connect, but it's always going to be an actual netcon. I'm going to be able to manipulate it, set the delay, set the wait, exactly the way that you'd expect. And even though this is an extremely simple model, you'll notice that I'm still building this using for loops and list comprehensions. Because I don't want to repeat myself, and I certainly don't want to say self.cell0 equals parameter 0, self.cell1 equals parameter 1. That's boring. And also because I might want to generalize this. What if I want to go from 2 cells to 3, or from 3 to many? So since I don't know what I'm going to want to do, I'm just going to go ahead and try to use for loops from the beginning so that everything is scalable. Again, as we've seen before, a synaptic weight of 1 is extremely strong with these cells, and the default. Remember, there's also a tau. So with the default time constant, we get these abrupt jumps. But in any case, so once I've constructed that network, I can then create that. N is my network object now. I'll go ahead and set up a stimulus to get the network going. say that it fires at 3 milliseconds. I'll set up my stimulus to go directly to the network synapse 0, the synapse on the 0 cell, and that has a certain delay, and again, a extremely strong weight here. I'll go ahead and record time, and I'll go ahead and record all of my membrane potentials. I'll construct my parallel context object. I will have a maxstep, initialize it, and solve it for 10 milliseconds. And then I can plot everything. And here we go. Now, if you're playing along at home, you may have realized that we haven't actually, so we're still, in fact, in this model, we're building a lot of parallel infrastructure. We're 90% of the way there. We haven't actually told it to run it in parallel. So this isn't going to run any faster. If we were running in parallel, and we had 2 different compute nodes calculating each time series, everything would work, except we wouldn't be able to record from both cells on the same processor, because one would have one cell, one would have a different cell. So we're going to have to do something about that. But before we get there, how do we generalize this? This is all fairly there. So I want to generalize this to what's known as a ring network within cells. And so your homework for today is going to be basically to do exactly this, except instead of a pyramidal cell, just do something a ball and stick. So a ball and stick model is a cell with 2 compartments, a soma and a dendrite. So we'll take the input on our stick, the dendrite, and that'll have like passive currents, and then our soma can have active currents, and then we're just going to build a ring network. This cell talks to this cell, talks to this cell, talks to this cell, and so forth, until you wrap around at the end of the world. The last and final cell sends its input to cell 0. So 0 talks to 1, which sends to 2, which sends to 3, sends to n-1, which sends back to 0. All right. And one of the nice things that Python allows is what's known as the modulus operator. So as I increases, for example, I mod n is going to go 0, 1, 2, blah, 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 n-1, but then back to 0. Modulus is just a fancy name for the remainder after you do division. So it's also, you could also think of this as clock arithmetic, right? We just wrap around when we're done. Okay, so how do I actually generalize to n cells in a ring network? Well, what I'm going to do is I'm going to just build in my network class, I'm going to build a list of all the netcons. I'm just going to loop over all of my possible numbers, and then I'm just going to say, well, GID connect cell I is going to send to, well, normally it would be the I plus 1th synapse, but instead I'm going to say the I plus 1th mod num. And again, as we saw, that's just going to wrap around, except it's going to be 1 off from I. So 0 is going to go to 1, 1 is going to go to 2, but n-1 plus 1, so num, I guess, minus 1 plus 1 is num. When I divide num by num, it divides evenly. The remainder is 0, so I go back around. So cell in num-1 is going to send to cell 0, otherwise every cell is going to go to the next guy. And again, I can construct a delay and a weight. I should really change this so it's not always using such a strong weight. And then I'll just, now that I've defined my netcon, I have to store it, obviously, because again, anything in Python that doesn't have a pointer to it, it doesn't have a reference to it, doesn't exist. And so now I'll just store that netcon that I create in my netcons array. And then I can go ahead. So now my network is parameterized with a certain number of cells that I want. So instead, it used to be pyramidal range for I and range 2. Well, now cells.cells is just however many cells that I want to have. So instead of I could have 2, or I could have 20. And here's what I get if I have 20 and I do the plot. Of course, you've probably noticed the immediate inconvenience of all of this. Namely that if I have 20 cells, it's going to be really hard to distinguish the cells when I'm simultaneously plotting the membrane potential. So what I can do instead is just store the spike times. And the nice thing is each cell already has a netcon in it that goes nowhere. Well, I can construct a vector for each cell, and each cell, then I can have my netcon record into that vector. So every time that netcon fires an action potential, I'm just going to go ahead and make a note of it in my netcon. And now I can loop over all of my cells. So for I, cell and enumerate my network cells, I can print out the cell identifier and the list of all the spike times. So for example, in my model here, cell 0 fires at time 4.6, 36.65, and 69.125 milliseconds. Cell 1 fires a little later, 6.2 milliseconds, 38.25 milliseconds, 70.75 milliseconds. Then cell 2 at 7.8 milliseconds, 39.875, 72.375, and so forth and so on. So now that I have this, I might want to store this in any of a number of ways. One possibility that makes for really convenient viewing if you're using a text editor is to store everything in what's known as JSON. And basically every programming language is going to have some library for working with JSON. So here, for example, in Python, the JSON library is called JSON. So I can import my library, import JSON, and then I'll construct it, I'll output to a file. So with open output.json, the W here is necessary to say that I'm writing to the file. Otherwise, Python will default to assuming that you're reading from a file, and then you can't write to it. So I can f.write. You can do this a little bit more efficiently, but this is, by the way, how you generally put anything to a file. So I'm showing it this way. So f.write whatever you want to put to a file. Well, what do I want to put to a file? JSON.dump to a string, dump s. And then I'll just go ahead and put my dictionary that I generated in the previous one. Well, I guess I didn't generate a dictionary, but effectively there's a cell and a spike times. So I'll put that expression, every cell, the ith cell, and here's this list of spike times. And then I'll go ahead and add some indentation just to make it pretty to read. The JSON libraries will all ignore the indentation. But so what this is going to do is this is going to put the same data in a structured format. It's going to look like this. This is a slight lie. There's actually an opening curly brace that's not shown here. But so the output.json is going to have a curly brace. 0 is going to fire at these times. 1 is going to fire at these times. 2 is going to fire at these times, and so forth. One minor nuisance is that you'll notice that the keys all end up being strings. No big deal, just be aware of it. Some languages care, Python cares, other languages don't. All right, but so in any case, so now we're able to store, we see at a glance, oh, if I want to know when cell 27 fired, I can scroll down to cell 27. Okay, in this model, I ran it with network of 20, so there is no 27. But you could imagine. All right. So then now that I have this information, I might want to plot this using, Now that I have this information, I might want to plot this using a raster plot. So just to illustrate, draw maybe a little tick mark at every time that a cell fires. And if I do that, you can do this in matplotlib with vline. If I do this here, cell 0 is firing at these times, cell 1 at these times, and so forth. And I see this guy fires and this guy fires, boom, 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 boom. And then eventually, once I get to my last cell, cell 19 is going to fire, and that's going to send a signal back to cell 0, and that's going to fire. And so I might use this kind of a representation to actually visualize the spike times. And I think I have code later on the slides, and if I don't, I'll post it for actually how to generate one of these raster plots. But before we do that, how do we actually decide? At some point, we still haven't actually told Neuron what processor is going to do what bit of work. So right now, we're still running single-threadedly. If we were to go back and run it with MPI, which is sort of the standard for multi-process communication, then every process would be doing everything. This is not helpful. So we need a strategy for distributing our load. This is known as load balancing. Ideally, we want every compute node to be doing about the same amount of work. And so one way of doing this is to just sort of pass around. This is what's known as a round robin strategy. So processor 1 gets cell 1, processor 2 gets cell 2, processor 3 gets cell 3, processor 4 gets cell 4, and then maybe we just start wrapping around if that's all the processors we get. So 1 gets 5 again, 2 gets 6, 3 gets 7, 4 would get 8. But now, of course, you could imagine that if we don't have 8, but we have 4, we have a bit of an inefficiency. And why is that? This distribution is somewhat inefficient, but it's really it's the best we can do without getting into what's known as multi-split. It's the best we can do with 7 things that you're distributing across 4 processors. They don't split evenly. That's where multi-split comes in again, but there's some overhead with that. But what this means, though, the fact that they don't split evenly means that processor 2 here has 2 cells it has to simulate, while processor 4 only has 1 cell. So processor 2 is going to take twice as long to get to all of those communication points relative to processor 4. Another way of looking at that is processor 4 is sitting around idle for a lot. Again, can't do anything better in this situation when you have 7 cells that you want to distribute into 4 slots. It just doesn't work. Somebody has to be doing an uneven amount of work. Nonetheless, be aware that this means that your speed up is going to be limited to, is going to be somewhat affected. You won't get 4 times speed up because the workload is not distributed evenly. All right, so how do we actually do this? So we can distribute our workload. Remember, set GID to node is what we need to do to tell Neuron that a certain cell is going to be simulated on a certain process. And again, so this is where you can use the GID check. Alternatively, you can do what I showed earlier with the cell class and just having the cell class be responsible for assigning GIDs as well. But so in any case, so what I can do is for GID in range, I'm going to start with my identifier. So imagine, okay, so here's how this works. Imagine that I have a certain number of processors that I want to run in. And so I'm running this with MPI, which I've maybe launched with Slurm if I'm using HPC, or just manually directly if I'm using my own machine. But in any case, so I've told the system I want to run with, I don't know, it's a good number, 16. I want to run with 16 processors. Okay, well then, so that's going to come in as what's known as pc.inhost. Again, PC is our parallel context object. So pc.inhost in that case would be 16. And I have so many cells that I want to run. And so what I'll do, in order to distribute this, every processor rather, is going to start counting from its identifier. So processor 0 starts counting at 0, processor 1 starts counting at 1, and it's going to skip by however many processors I have. So this counts from the identifier up to however many cells I have, skipping along by however many processors I have. And so everybody ends up with the correct identifiers. Everybody claims their cell identifiers. But, and this is a nice thing, and this is where it begins to get really pretty, each processor only has to calculate, at most the ceiling of the number of cells divided by in-host cells. I don't hit every single one. I'm literally just doing my part of the problem. So in our case where I had 7 things to distribute across 4 processors, now if I'm using this rule to distribute my cells, and so in this ... here is the part where I actually construct the cells. If I'm using this rule to distribute my cells, then every then I, in that case where I had 7 things across 4, I'd only actually even bother constructing 2 cells at most in any given processor. Now it so happens that, of course, not all cells are created equal. And what you really want to do is you want to balance the amount of work that you're doing, not necessarily the number of cells. I wouldn't start out with this, but I would if it proved to be a problem. All right. So how do we actually do this? If it turned out that there was this really large imbalance, and not because the cells couldn't be balanced, but maybe because imagine a world where I have one cell has 10,000 compartments and everything else is point cell models, right? In that case, I don't want to say, distribute all of my point cell models evenly and also have one processor that's tasked with this 10,000 cell monstrosity or 10,000 compartment monstrosity. What I'd actually like to do in that scenario is have the heavy load on one processor, because let's assume we're not using multi-split, the heavy load on one processor and let all of the other ones deal with the small guys. And so what we can do in Neuron, if this comes up necessary, and again, this is not always necessary, it's probably rarely necessary, but it depends on your model, we can actually estimate the amount of work instead of the number of cells. And so the way that we do this, we might distribute all of the cells because we got to construct them in order to analyze them. So we'll distribute all of our cells round robin to the processors as before. We'll instantiate them. And then we'll go and we'll calculate the computational complexity. And Neuron has the library for this, known as the load balance library, or loadbal.hope. So I can load that file in, that's the load balance library, construct a load balance object, and then just use that load balance object's cell complexity method to calculate and pass in a section, any section on that cell, and it's going to calculate the complexity, computational complexity of that cell. It's going to take into account the number of segments, etc. And then this is going to return a number. And then so I can distribute sort of based on the computational complexity. Well, how would I do that? Well, okay, first of all, go ahead, destroy all the cells. We're going to send all of the computed complexity data to one compute node, or it doesn't have to be, could go to all of them. But let's say we're sending it all to node 0, and the parallel context object has methods for that. But this is basically an MPI altogether. And so then on node 0, then we'll distribute GIDs, and we're going to just sort of keep track of the amount of work that's assigned to every processor. So the next the next cell that I'm going to process is going to go to whatever processor has the least amount of work to do so far. And you could optimize this further. And again, this introduces overhead itself. But if you're able to sort the amount of complexity, all right, go ahead and distribute the big things first, and then work your way down. And if you distribute, and then that'll give you a decent estimate of a reasonably efficient allocation of resources. And there's theories that'll go and tell you the upper bound for the worst case scenario, but it's not too bad in terms of how well this will do versus the theoretical optimal balancing. But so then you send the GIDs to the nodes, or again, if all the nodes have this information, they can just keep track of everything, who does what, and then just build their own stuff. But either way, once all the nodes know this, they can instantiate the cells. I should also point out that this is a relatively simple estimate of cell complexity. Neuron also provides some other more complicated estimates of complexity using load balance experimental Mac complex. And again, you can look for, you can ask us if you have questions about these things, but these are probably not going to be needed for your model. All right. So in fact, this is so not going to be needed for our model. I'm not going to address this any further. If you have more questions, again, please press ask on Ask Tutors channel on Slack. But how do we actually parallelize this? So let's do it. Let's actually run something in parallel. Okay, couple of things that we have to do first. In order to do this, we're going to need to initialize MPI. MPI is sort of the communication library for parallel computation, parallel process-based communication. And so in Neuron, we can initialize MPI using h.inner and MPI underbar init. If you know Python, you like MPI for pi, you can have MPI for pi, initialize MPI. It really doesn't matter. This is not a Neuron specific thing. It's just it's a requirement imposed by the MPI library itself. And we're just going to, Neuron provides a way of doing it, but any way of doing it should work. All right. Finally, in order to do this, well, almost finally anyways, we're going to need to have our network cell, our network class is now going to be modified slightly. And we're not going to construct all of the cells in our network. We're only going to construct the ones that our individual compute node needs to know. So the way that we do this is I'm going to just start counting, again, as we said, from my current identifier, my process identifier, up to the number of cells by the number of processors involved. So again, in our case, where we had 4 processors, maybe I go 1, 5, 9, 13, and so forth. And I will construct those cells, just those cells. But you'll notice that when I'm doing this, I'm still using the identifiers, the global identifiers. I'm not constructing pyramidal cell 0 and then pyramidal cell 1. I'm constructing whatever pyramidal cells and their identifiers that I need. I don't have to make any changes to the cell class, right? It's only a statement about my network itself. That's another reason to sort of segregate out the cell class the way that I did, right? The cell class doesn't care about the networks, the parallelization. All right, and finally, so here, when we actually do our connection, we're going to connect. So this connection part is different. We're going to connect it using ParallelContext.gid connect. But here, this is our slight gotcha. Instead of doing, we're going to have to write this as how do I want to say this? The postsynaptic side is the one that needs to own the netcon, because the postsynaptic side is the one that's receiving a thing. It has a synapse for it to go to. And so now instead of I is going to go to I plus 1, we really should probably think of it as I minus 1, wrap around with the modulus operator. So I minus 1 mod num is going to send to our synaptic object. And this again has to go on whichever one. This has to go on the postsynaptic side, because otherwise there is no synaptic object to go to. So I minus 1 is going to go to the ice cell synapse. But otherwise, the network stays exactly the same. So very, very minimal changes to our network class were necessary to go from parallel to the parallel version based on what we had just sort of put together. All right. Finally, the one other change, in order to actually get our cell to do anything, we need to have, in our network to do anything, we need to stimulate the network. That's all exists before. But we only do this on the network, on the compute node that owns the 0 cell, since the 0 cell is the only one that's getting the stimulus. So there, I will add this extra little if statement. If we own the 0 cell, then construct a stimulus and hook it up to the 0 synapse. Cool. So this will now run our simulation just fine. If we want to actually write our data, we don't want to dump to output.json, because now, for example, our 0th processor might generate one set of outputs. Our processor number 1 is going to have a different set of outputs. So what we can do, and this is again not using the f-string syntax, but this is another way of putting the processor identifier into the location. So this will generate multiple files. will generate output 0.json, which is whatever cell 0 computed, output 1.json, whatever the output, cell processor, sorry, output 0.json is whatever processor 0 created, output 1.json is whatever processor 1 created, and so forth. So now, for example, when I'm actually generating my JSON, I will instead of just iterating and enumerating, I will just grab the GID and go ahead and use that to key everything. So that way, all of my information, collectively, I have everything, but I don't necessarily have it on any individual processor. All right. We could, as an alternative to the per processor writing, and the efficiency of all of this depends on sort of how the HPC, if you're working in that, is set up. But the alternative is to use ParallelContext pi all-to-all, and if you're using MPI for pi, that's cool too. But in any case, it would then be a MPI all-to-all, and then we could send all of your data to node 0. So generate all of your pieces. Pi all-to-all will send whatever local data that you want, and then just a whole bunch of nones to all the others. So none of the other processors get anything, but processor 0 gets everything. Or you could send everything to everything. That's cool too. But really, there's no point because only one processor. If one processor knows all of the spike events, it's able to generate the file, and then there doesn't have to be any. Processor 1 doesn't need to know. Who cares? Because we'll still have our data. So basically, what happens is then, if we are sending everything to processor 0, then we'll have processor 0 and only processor 0. So we'll check our processor ID using pc.id. If pc.id is 0, then we'll just sort of aggregate. We'll get all of the data in the all-to-all, and then we'll just sort of collapse it down into one dictionary by just constantly updating it as we grab each piece. We'll update that dictionary with what did I know from processor 0? What did I know from processor 1? What did I know from processor 2? I'll build up everything, and then I will have a single dictionary, and then I can use my JSON as original and generate a single file. And then that's basically it. You can run this using MPI run or mpiexec. So you type, for example, MPI run -n4 to run with 4 processors, Python, and then my script, let's say myscript.py. And then it'll run this with 4 processors. If you were to go back and run it with 2, everything would still work. You should still get the same results. And then if you're using certain machine architectures, you'd need to use, if you're using a shared system like Slurm, you'd have to use a couple of extra lines with Slurm to set up your job. But in any case, this will run, this will generate all of the data, and it'll store it in a single file. All right. So performance-wise, how does this work? Well, so it really depends on the scale of your model. The fundamental thing so we've done a whole bunch of experiments taking simple models and scaling them up. And what you'll see, I mean, we can neuron scales to, potentially thousands of processors if your model's big enough. But when the number of cells starts to be on the same sort of order as the number of processors, then you're not going to get a linear speed up, and you're going to start to see the effect of load imbalancing. And that's just the way it is. But neuron, as long as your processors are, you have significantly more cells than processors, you're going to be able to distribute it fairly well. You're going to see decent near linear speed ups, or you'd expect to see it anyways. And this scales, and we've also looked at, don't worry too much about this, but there's a paper if you're interested that looks at how different scaling strategies, different communication strategies work with spike exchanges. And there may be occasions where you don't want to do this all-to-all communication. You want to have So Neuron's default is to just have every cell send all of its information, every compute node send all of its information to every other compute node. Because generally, if you think about it, you have a large network. You have thousands of synaptic inputs going in. You're probably getting input from all of the cells, or if not, maybe, well, certainly not all the cells, but every compute node may need to know all of the cells. So you might as well just send all to all. Otherwise, you incur a lot of overhead and you incur overhead in who gets what, and you're not actually throwing away too much information. Again, the exact details are going to vary depending on your network architecture, and in fact, also the HPC architecture. But Neuron's defaults do a decent job, but you can check out that paper if you're interested. One other pro tip, we talked about last class, we also talked about variable step versus fixed step simulation. Remember, variable step exists to choose the time steps based on the numerical accuracy that's required. And what that means, though, in a network model, is it's going to try to get the exact spike time and deliver the spike time at the exact right time. And that's all well and good if you have only a couple of cells, but if you have a large network, there's basically a continuous stream of spikes. If there's a continuous stream of spikes, in order to get all of those spike times, Neuron's going to have to be like, well, okay, well, I'll simulate it this time, and I'll simulate it this time, and I'll simulate it that time, because there's a new spike, there's a new spike, there's a new spike. And it'll get the accuracy, but it'll use these super tiny time steps. And so oftentimes it's much more practical to use a fixed time step advanced, even though you introduce a small amount of artificial synchrony in your inputs. But hopefully if your time steps are small enough, this is not actually a major problem anyways. All right. So now let's look. So we've been talking about storing spike times, but what if I want to go back and I want to know the time series of the M variable at the center of the soma in cell 5? I don't have to rerun my network model if I've saved my spikes. And it's just these sort of event-based communication. Because that's all that the cell needs, right? If I know my initial conditions and I know my events, then that fully defines the neuron dynamics. All right. And we talked about this very briefly last class and over Slack. What we can do is we can use vecevent.mod. You can search for it on GitHub. Alternatively, it should be on your computer somewhere. You can search for it. Like I said, you can search for it on GitHub. It is not in the built-in libraries. It's in fact one of the neuron examples. But with a vecevent.mod, or honestly, just a netstem, if there's a small enough number, a whole bunch of netstems, if there's a small enough number of events, you can trigger the cell. So here's how we do this. So let's say that I'll load my JSON library. I'll set up my model as I would before. I'll read in my data from my output spike times. But now if I want to get just the particular value of M from one gating variable, I'll construct only that pyramidal cell. I don't need to construct the network. I'll construct only that pyramidal cell. Yeah, I'll figure out who all it's connected to. Vecevent.mod gives me this thing called a vexstem. And what I'll do is I will go ahead and pass in all of my presynaptic cells, spikes. Certainly don't care about the postsynaptic cell spikes, but I'll pass in all of the presynaptic cell spikes. I'll throw them into a vector. And I know what they are because I saved all my spike events. I'll throw the presynaptic cells into a vector, and I will do a vexstem.play from my spike vector. And then that's going to set up my vexstem to fire an action potential at every time that the presynaptic cell fired. And so what I'll do is I'll now go ahead and connect my create my synapse on my cell. But instead of connecting it to the presynaptic cell, because the presynaptic cell doesn't exist, I will connect it to the vexstim. So those the times that, so it's an event that's going to fire, it's a stimulus that's going to fire every time the presynaptic cell fired in the network, even though I'm not even simulating it. So now I'm going to get the exact same inputs to the same type of synapse on my cell that I'd get if I was doing the whole network simulation, but now I don't need the whole network simulation. So now that I have that, and set up my netcon exactly as before, I can go ahead and record whatever I want. So I'll record time and I'll record my M gating variable. That's cool. This is an alternative synapse. I should adjust this to the way that I've been doing this for the rest of the course. So p.summa square bracket 0, 0.5 .hh._ref m would also work. But so in any case, you can go ahead, record my spike, my gating variable in this case. I go ahead and run it as before, ParallelContext, maxstep, initialize, run. And now I have it. I can just call my function and I can say, okay, tell me what cell 5's M gating variable was. And then I'll have my time series and then I can plot it. But I could just as easily go back and grab cell 2's or, cell 7's, cell 396. I don't have to simulate the entire network. All right. So let's talk about pseudo-randomness. There's a lot of reasons why we might want randomness in our model. We may have a stochastic input, right? So we may have spikes that arrive according to some Poisson process. We may have stochastic channel gating. We may have random channel parameters or random morphology or random network connections. Fundamentally, though, we're going to want our random numbers to be reproducible. And one of the ways that you make them reproducible in a single process system is to just have a random seed and always pill them at the same number. So if I start random seed of let's say 5, then I'm always starting my random number generator at the same point, and I pull all of the numbers in the same order, well, then everybody's going to agree. No problem. But in a parallel context, that doesn't work because if I have if I have one compute node of 10 compute nodes, is going to make a difference into which random numbers I pull, right? So in order to do this, we need to introduce some more parameters into our randomization. And this is non-trivial for reasons of making sure that mathematically the random numbers are all independent. So you can't simply advance, it would not be correct to simply advance the seed by a large number and then start pulling because they're now still within the same stream. Fortunately, there's a number of parallel random number generators that exist. Neuron uses one called random 123. Here's the paper, Salmon et al. That describes this random number generator and proves that it is, you have independent, reproducible, restartable streams. So in particular, the random 123 is going to give us 3 parameters to use. You can think of this as a seed and 2 identifiers if you want. So let's say that I want to have random synaptic inputs. I could construct my random number generator, give it so this is a Poisson process, right? So negative exponential delays. So I will construct my random number generator. I will specify the distribution that I want for my random number generator. And then I will switch my random number and I'll specify the rule at which I want it to use. So I will use a random 123. And here are my 3 parameters that are defining my random number stream. So now what I'll do is I'll construct my netstem. And now my netstem has a method that we've never seen before, which is noise from random. And then so my netstem will use this random number generator that I pass in to choose the intervals between my spike events. And so this way, as long as I'm constructing random 1, 2, 3s, the same parameters to construct my random number generator, I will always get the same results. So how does this help us? Well, it helps us because we can use one of these identifiers as seed. We can use one of these identifiers to indicate which cell we're working on. And so if cell 5 always pulls from a random number stream, where let's say the second parameter to random 1, 2, 3 is 5, then it's always going to get the same numbers regardless of which processor it's on, because it's the only one pulling from that random number stream. So every pyramidal cell object will have its own random number stream. And we could do this, not just in the level of a cell, we could do this on the level of the compartments within the cell if we wanted to. We wouldn't really have to unless we were doing a multi-split scenario where we're breaking the cell into pieces. But we could, here, for example, if I want a random distribution of leak conductance, I could generate a new random number stream. And so here, for example, that just takes an identifier. But so maybe I'm going to use my global seed, my GID, so my cell identifier, and then just an identifier as to what section I'm looking at. And I'm looping over all the sections here. And so this is going to give me a whole bunch, give me a different random number stream for each section. And now each section could set up independently and pull whatever variables that it wants. So here, for example, I'm grabbing a truncated normal, basically, that never goes below 0 for each section. It's not a whole lot of advantage to this, to splitting up on the level of sections, again, unless you want to do the multi-split method and split a cell across multiple processors, but that introduces significant overheads that may not be worth it even then. But at the very least, it's extremely useful to be able to grab a random number stream that is on a per cell basis. Because that way, every cell does the same thing, no matter how it's distributed. All right. Let's talk briefly a little bit more about load balancing. Or not. So this is all basically things that we've already seen. One alternative that we haven't discussed is random allocation of GIDs. And every processor can make its own distinction if they're using their own identical random streams to decide who does what. And so this is another alternative. And again, it can be done if every processor uses the same random stream to choose allocations, then they're all going to come up with the same thing, and no explicit communication is necessary. All right, 2 items that I want to touch on now, finally, before we actually do this, before we end for today. So let's talk about multi-split. So the idea with multi-split is I may have a single cell that is extremely complicated to simulate. So here, for example, I have a Purkinje cell. It has a number of compartments. And what Neuron allows you to do is to break. You can specify a section. You can specify a segment, actually, and you can say that I'm going to break the simulation at a specific location. And one processor or thread, actually, this works with both threading and processors, is going to do the calculation on one part of the cell, and one processor is going to do it on a different part of the cell. And there's certain restrictions as to how things get distributed up, but basically it has to be a tree. Now, if you're doing this in order to get this efficiently, if imagine that I have 4 CPUs. If I split this into 4 pieces, that's all well and good if the pieces have comparable computational complexity. If they don't, I'm actually better off if I'm going to take the overhead of communication anyways. I might as well split it into more pieces, so maybe 16 pieces, and then I have some flexibility as I distribute. I'll do load balancing across each individual, as how the pieces are distributed, so I can get even more efficient distribution of the parts of the cell, just like I'd want to get efficient distribution of the cells. All right, and the algorithms described in Heinz et al. 2008. Here's the DOI. You can look it up. But fundamentally, what's happening here is that normally you have what can be thought of as a tridiagonal matrix. Obviously, branch points are a complication of this, but as Heinz 1984 showed, you can actually structure basically tree matrices, the kind of matrices that you get from a neuron, in ways that can be solved in the same amount of compute time as a tridiagonal matrix. And this remains true with a multi-split. So we can take our tridiagonal matrix, split it up into blocks. Each block gets solved individually. But of course they can't be completely separate. You can clear, say, below the diagonal everywhere, but if you're trying to do this and you don't know all of the information from the previous cell, from the previous matrix, you actually can't literally clear below the diagonal. Best you can do is create these N-shaped matrices. So you do all of this, you try to clear things as best you can, you create these N-shaped matrices, and then you send the information just at the corners of each matrix. That's enough to allow the matrices to be, each matrix to be inverted itself. So then you go back and you do another pass of row reduction, basically, and then you're able to invert the matrices. And if that didn't make any sense, check out the 2008 paper. But it really doesn't matter. Neuron's going to do all of this for you. Neuron's going to do all of this for you. But it does sort of illustrate that there's actually we've gone from, instead of having a single pass of integration, we have a single pass of matrix inversion. We do one pass, we do a communication event, and then we do another pass. So whether or not this is going to be efficient and actually make things run faster for you is going to be dependent upon the nature of the problem itself. But if you're using the graphical interface and you just want to use threads, you can actually pull up what's known as the Parallel Compute Toolbox. You can look for it in the menus. And so you can click, I think it's refresh, and it'll calculate an estimate of the number of processors that you have. It'll analyze the model complexity, and it will give you this lovely little checkbox here. And if you, in the graphical interface, if you check the multi-split, it'll use threads to simulate a single cell in parallel. Now, this isn't going to quite solve everything for you if you have a big network model. For that, you're going to have to write code. But this will give you a sense as to how an individual cell might split and how efficiently an individual cell might split. When it comes time to actually doing this in the network, you have to declare the split points explicitly. You do this with ParallelContext PC, your ParallelContext object.multisplit, and you just pass in a segment and an identifier for that. And that's going to be the point where we break everything. Once you've declared all of these split nodes, every process runs this pc.multisplit call with no arguments. and that will actually set up the communication so that everything happens going forward. And at this point, if you have created the entire cell, so sometimes you might do this by creating the entire cell and then just throwing it away, now is the time to throw away the parts that you're not actually simulating. There are a couple of rules you may have noticed from the matrix process. It can only connect on 2 points, right? So every subtree can have at most 2 split nodes. And there are certain things that this does not support. This doesn't support variable step. This doesn't support linear mechanisms. This doesn't support extracellular or reaction diffusion. And once you've made the split, you can no longer use things like h.distance because, as you see, if you've destroyed the parts of the cell that don't belong to the processor, well, then there's nothing to compute the distance to locally. And again, just as to state this explicitly, if you're doing load balancing, it's in order to get good load balancing, it's often going to help to actually split the cells into more pieces than processes. If you want an example of this, I think we've seen this video before, but this is you can look at Michele-Maiori's 2014 paper. It's on ModelDB entry 151681. In particular, there's a file there called multisplit distrib.py, and that shows an example of using Python to set up a multisplit simulation. And the reason they do that is because they have lots of relatively inexpensive granule cells and some mitral cells that are much more expensive to compute. And then so you multisplit to speed up the simulations there. And finally, I want to end by talking about gap junctions, and implicitly, and this also is basically true for any other reason that you'd have continuous information exchange. We saw before, I think, what was known as the half gap method. And so the half gap method used pointers, right? And so we could construct a gap junction by saying, well, okay, well, what's the potential on the other side? What's my potential? I'll use Ohm's law to calculate the current. But in order to do this, we had to have pointers. Pointers, require the thing that we're pointing to exist on our compute node. But in a parallel environment, it might exist on our compute node. It might not. By the way, fun fact here, there's nothing that says that everything, all of your events, all of your communication has to be done using MPI. If you happen to know that everything is local, you can skip all of this parallel context bit for that which is local. And there might be times, for example, if you have a small subset of cells that are communicating using gap junctions, if you could put all of those into one processor, then you wouldn't need to communicate every single time step because you wouldn't need to use the parallel context infrastructure for doing so. But in general, that's not going to be the case. So what can we do instead of pointers? Well, we'll use the same trick that we did with cells. We'll assign an identifier for each location. So here, for example, I'll declare a source variable, and my pointer will get an identifier of 1 on cell 1. And my corresponding pointer on the other side might get an identifier of 2. Now again, I'm not guaranteeing here that they are on different processors, but this way is a generic way. It doesn't require me to think about who owns what. Ideally, we want to have all the code not have to think about it, not have too many exceptions. We don't want special cases or places for errors to sneak in, right? So what we'll do here, instead of assigning a pointer to a value, we'll identify you will use parallel context object to identify a number. We're going to read the variable, and sort of analogously to defining a source variable, we'll define a target variable, which is going to have the exact same syntax, except now our pointer is going to get the values from cell 1. And that's it. And then we'll do everything else that we've done with our simulation. But now the parallel context will be responsible for synchronizing the pointers. I should point out, to the mod file code, they now become a range variable instead of a pointer. But that's it. And then so we can take this and we can run the simulation, and it'll, with minimal changes, all of our regular MPI stuff works, and it's great. This is just another example showing, and we still can get near linear speed up with, say, the Traub model and hundreds of processors, even with gap junctions. So here there's 3,500 cells and 3,500 gap junctions. But we'll never get the same kind of performance benefit because we're now doing more computation. And multi-split can help, but multi-split doesn't cure everything. And finally, just to end for today, you can actually combine parallel simulation with parallel bulletin board parameter search. Again, you're probably better off not doing this. You're probably better off doing just the bulletin board style or multi-processing even style of parameter search, wherein you do one process, does one calculation in serial, because that way you don't have to do any communication. But if you wanted to split things into pieces, basically it's pc.subworlds is going to allow you to split everything into two worlds. And then then each one is responsible. So the all-to-all communication is now, well, it's all-to-all within my little subworld. I'm going to talk to my friends, but I know that there are other nodes and I have no direct interaction with them. But again, unless you're dealing with memory on a single node being a limiting factor, you're either going to want one subworld, which is everything. Everybody talks to everybody, or pc.inhost subworlds, in which case everybody is completely independent. But it is an option for certain simulations, be able to do both. And a split, so this is going to run two parallel simulations simultaneously. Note that if you want, suppose that we actually want to run a simulation. So let's suppose that I've defined a thing called my model, and I want to actually run this. So I would generally say mpiexec -n4, let's say, would run on 4 cores on my, this is running on my local machine, obviously. Then I will just launch it as normal. So Python mymodel.py. And then I'd hit enter and I'd run. And if I got an error message from this about mpiexec not being found, there's two options that I can do. mpiexec is the standard. Sometimes, for whatever reason, you might find it still doesn't exist. If mpiexec doesn't exist or doesn't work, you can always try mpi-run instead. But I think that's mostly an artifact of the past. The second thing that I want to point out here is that you may not have MPI installed. So if you get an error message from that and it doesn't know what mpiexec is, go look up how to install MPI on your system. If you're using Conda, I think that you can, if you do a Conda install MPI for Pi, and I'll just show you that, I think that will set you up with a working MPI installation, but you're going to have to check that. And I'm not going into details here because Linux and Windows and Mac all have slight differences for this. The other thing is, of course, the homework. So for Thursday, I'd like you to try and construct a network of n-simple cells. And again, we saw that it's nice to be able to test this with a small network and then scale it up to more and more cells. And instead of trying to do this pyramidal cell thing that we did in class today, just imagine that we have two sections, a soma and a dendrite, okay? And just connect them in this sort of circular fashion, this ring fashion. Start the activity in the network by giving a stimulus to cell 0, get the cell to fire. And then so hopefully if everything, the synaptic weights are in the same certain regime, then, cell 1 will fire, then cell 2 will fire, then cell 3, and so forth back to 0. So make it happen. Make it happen in parallel. Visualize your results. Yeah. And finally for today, I promised I'd show you how to do a raster diagram. So here, imagine that I have a list of vectors of spike times. So here, instead of a dictionary, I've the 0th. I have a list spike times, and the 0th element is the times that cell 0 fired. The 1th element is the times that cell 1 fired, and so forth. Here's a little bit of code using matplotlib that will show the spike times. And with that, I thank you for your attention. Any questions, please ask on Ask Tutors, and we'll take them up, of course, on Thursday when we'll talk about solutions to last Thursday's and today's exercises. Have a good one.